On this installment of MatHAMMatics, we are going to take a look at the introduction to coordinate geometry by looking at triangle properties and exploring some principles around the Pythagorean Theorem. All right, well, as promised in today's episode, we're going to dive into the introduction to coordinate geometry. Coordinate geometry, very creatively named by very creative mathematicians. Coordinate being on the coordinate plane, geometry meaning we're going to be dealing with shapes. Like we did in our last unit, we're going to be looking a lot as we go forward as to whether or not we can determine congruence between shapes using their coordinates. Full disclaimer that if at any point you hear loud noises, my children are playing Connect Sports in the basement, and they're just going to happen. So let's dive in. Before we really work the coordinate plane into our geometry concepts, it's going to be really helpful to have a generic understanding of some triangle vocabulary, right? We spent a lot of time in our last geometry unit looking at triangles. Here we're going to give some specific vocab names like we often do in the first lesson of a new unit. So on your note sheet, you'll notice that we've got 3 different triangle types. And the first set of vocab we're going to look at are angle-based vocabularies. First one here, you'll notice we have the right triangle. Right triangle, very creatively named again, because it possesses one right angle, right? So as long as a triangle contains a right angle, it will be considered a right triangle. These do not have to be identical in order for them to be a right triangle. That just happened to be the way this one drew up, okay? So right triangle has a right angle. Makes sense. Acute triangles, oddly enough, have acute angles, right? Notice that every single one of these angle measures is between 0 degrees and 90 degrees, right? That's true for 66. That's true for 49. That's true for 64.9. So an acute triangle means all angles are acute. Lastly, obtuse triangles, described by having, you'll notice 2 of these angles are not obtuse, right? This is acute, and this is acute. Well, those of you who are still following along here at home may notice if we were to have more than one obtuse angle, we wouldn't have a triangle anymore, right? Because anything that's bigger than 90 plus anything bigger than 90 is going to be bigger than 180 degrees. And by definition, right, the angle measures of a triangle always add up to 180 degrees. So obtuse doesn't mean that every angle is obtuse, but instead it possesses, right, or just like the right triangle, it contains one obtuse angle. Okay? So there's your right, acute, obtuse. So if we're able to determine what the angles are, it's pretty straightforward to figure out which of these 3 triangles we're working with. Now, one of the things that you may have had some experience with in middle school or in a previous math course is the idea of the Pythagorean Theorem. Right? So the Pythagorean Theorem, which is attributed to Pythagoras, which is a Greek scholar, determined that if you have a triangle and you take the leg, I guess I should specify that too, right? Hopefully we're familiar. The leg of a right triangle are the non-longest sides. one of the things that we always know to be true, right, is that side opposite an angle correspond in size. Well, what do I mean by that? Let's take a look really quickly at a triangle here. See if I can make myself a little triangle right here, okay? The magic of technology. Let's give this a color we can see. Oops. How do I color this? Maybe it's over here. Okay, no idea how to change the color on this, so I guess we'll try a different one. Guess technology isn't as magical as I'd hoped. All right, there we go. There's one that we can see. So now, if we were to think about the side lengths of this triangle here, I just need you to go and hide for a minute. There we go. So let's think about this triangle and let's give it some names here. So we'll give each of the vertices of this triangle a name. We'll call this one, and let's go D, E, F. Okay. Well, one of the ways that triangle side lengths are often named, right, is that if you have a capital letter as the vertice, right, or representing the angle, then the opposite side will get the lowercase letter option, right? So we could think of this as D, E, or F. Well, in this particular triangle example, let me move this out of the way so we don't run into some trouble there. All right, side E would be the longest side. Because it is opposite the largest angle. Okay? Opposite the largest angle, right? So this is the biggest angle of the three, which means that side length E would be the longest side. And that speaks directly to what we're getting at here in the Pythagorean theorem, okay? So here we have a leg, right? This is one of the shorter sides. We have a second leg, right? This is, again, one of the shorter sides because these are opposite the two smaller angles. And in a right triangle specifically, the longer leg is known as the hypotenuse, okay? So Pythagoras determined, or is attributed with determining, that if you take the square of each of the legs and add those together, right, this a squared, you may have seen this as a squared plus b squared, then this sum here is going to equal the square of the hypotenuse. Or often it's known as a squared plus b squared equals c squared. Now, one of the ways that this works, or the reason that this works, right, is that these relationships between the sides happen to match up nicely with this rule about a right triangle, okay? And so what I have for you is a quick Lego illustration of how the Pythagorean theorem works. So if you notice here in this Lego illustration, I have a 6-sided, an 8-sided, and a 10-sided triangle. And if you line up the 6 side, the 8 side, and the 10 side together, it forms a right triangle. We'll notice too that what we have in these Legos is the 6 being squared, right? We've got the 6 by 6. We have the 8 being squared. Those are our 2 legs, right? Or the 8 by 8 right here. As well as the 10 by 10 squared, right? Well, what happens if we try to add a squared plus b squared? Let's take a look. And so we can see that if you add a squared plus b squared, it does in fact equal c squared. And so this leads us to one of these principles, that if you know the side lengths, right? So if we know the side lengths and option 1, a squared plus b squared is equal to c squared, then we know it's a right triangle. But what about if a squared plus b squared is larger, right? What if a squared plus b squared is bigger than c squared, right? What would happen then? Well, if a squared plus b squared is bigger than c squared. Well, let's take a look at this situation here. Notice I have a circumstance here now where the sum of a squared and b squared is now bigger than c squared. Well, what kind of a triangle does this produce? Let's take a look. We'll take a look at the angles that are being formed by this triangle. This, in fact, leads us to, right, or we have an acute triangle. And so what would you then suspect would be the case if c squared was bigger than the sum of a squared plus b squared? Well, here's the illustration. Notice that a squared plus b squared is smaller now than c squared. And when we run this, we can see, in fact, that we have an obtuse triangle. And so now, if we know the side lengths, we can also determine right away whether or not a triangle is right, acute, or obtuse. Simply take a squared plus b squared and compare it with c squared. If it's equal, we know it's a right triangle. If a squared plus b squared is larger, we know it's acute. And if a squared plus b squared is smaller than c squared, we must have an obtuse triangle. Well, some other pieces of information that are good for us to have definitions for are these 3 terms, right? Or types of triangles that are defined by their side lengths. The first one we're going to take a look at is a scalene triangle. And what do you notice about these 3 side lengths? Well, all 3 sides are different. So a scalene triangle, by definition, means that all 3 of the side lengths measure differently. What do you notice that is different about an isosceles triangle? Well, now all 3 sides are not different, right? We have 2 congruent sides. Okay, right? 2 of these side lengths are the same. This one is not, right? Or we might mark this triangle up with our congruence markers. And one other property that's really helpful with the isosceles triangle is that when you have 2 congruent sides, the angles at the base of an isosceles triangle are also congruent, right? So not only are the sides congruent, but the two, what we would call base angles, are also congruent. All right, so lastly here, we've got the equilateral triangle. Here is a pretty simple representation. Equilateral, equal sides, right? So all three sides are congruent. And what that's also going to mean, right, is that all three angles are congruent. And since a triangle sums to 180 degrees, we also know exactly what that measurement's going to be, right? If all of these angles are congruent, well, that means that each angle will represent 1/3 of 180 degrees, or each angle is 60 degrees. So using this information, see if we can tackle our practice problems for tonight.